Anton Mellit. So take it away.
So I had some discussions, and after that I fixed my plan a little bit more. So part 3 will be on P equals W conjecture, and you can treat the part 1 and 2 as some sort of spiritual introduction. But, so last time I want to remind for people who, for instance, who were absent, I introduced, we have G in, I diagrammatics. I introduced diagrammatics of SN and the Hecke algebra type of type PLN and UQ GL. Well, this is a different M. So it was in the same framework where you remember, like, there were this kind of lines. They had thickness, and then operators I looked like this, and operators Fi looked like this, and then and sigmas were defined for the case when all 1 AM equals to 1, and then M equals N. Then they satisfy this. The picture of sigma I is this. And they were actually defined as Fi EI minus 1. I don't make a mistake. And they satisfy this relation. And then the second part was, and then I explained that there is a calculus of flags over the finite field, which gives all these maps natural interpretation, satisfying all the necessary relations. So in particular, whenever you see something like this, means forget step in the flag. All right, if I have first, if I have something line like this, means the jump A, and the jump of dimension equals A. This means forget step in the flag, and this means introduce it in all possible ways. Always. And then, yeah, then if maybe I will write down information of the ordinary cell relation. Just to think it was hope I put it in my order. Okay, so that's sort of the calculus, and so let me start with making some observations. So whenever you have some sequence of generators corresponds to some picture. For instance, imagine you have something like E1, E2, E1, for instance, right? You have this one, then this one, and then this one, then you can stare at this diagram and realize that actual actual regions in this diagram, for instance, A1, A2, A3, correspond to subspaces over a given vector space. So for instance, here we'll have F1, F2, F3, F4, and F5. So regions correspond to subspaces. And when regions are connected, then they correspond to embeddings of subspaces. So as regions touch each other, means embedding of subspaces. Okay. And then, okay, and then the matrix coefficients of any element are number of points of some configuration variety. So of flags matching this conditions that they have to embed. Spaces should embed into each other.
This is all over of Q.
Yeah, number of points over of Q.
I'm sorry, so to what do you associate a matrix or a matrix coefficient? So to a region, you
Well,
associate a vector space.
If you you just fix flags in the beginning and fix flags in the end. Let's count how many times we can get from one to another.
Would you say that generally, if you take a red chalk and draw a closed surface on this picture, then to that closed surface, you would associate an, closed curve.
So this admits natural generalization. So right, that's natural generalization is that you look at, for instance, you can draw these pictures on surfaces and again get varieties, and that's what Lev is saying. So we can draw pictures on surfaces and try to make sense of them as varieties. Of them as varieties. And let me just tell you what you get if you just draw it in the annulus. For instance, meaning that you just close this up, closing diagram up, meaning you have this diagram and I don't know, some operators, and then close it up. So this is just one puncture. So you have here 0 and then here 1. So the dimensions, the numbers are dimensions. We get some, this produces a variety. And then you can, well, as I explained, you can count points on this variety, or you can take its cohomology of this, and that's one way to so sort of extending this construction, you can define the Hawano homology over link. Is one of Rozansky Lansky
This would give
homology.
triply graded.
Yeah, overlink of the closure of the triply graded. So that's sort of one piece of one idea I wanted to explain. And here you can do this both in the UQGL setup and in the Hecke algebra setup, using different sort of diagrams. And
You wanted to, if you wanted to do this not homology, I'm just saying a little more fancy, you have to turn these fractions into complexes.
right, so yeah, well, there is very easy way to interpret. As I said, so the whatever I did, well, okay, I didn't say what is a variety. If you so when you have this picture, it means that you merge and then split and subtract one. That is interpreted as a set of as a condition on the flux that they're different in one step, but inside in all the steps. That's what I said last time. And so this is still a number of points on some variety, and you take a homology of that variety. That's what I mean. But if you really want to be precise, you only get some top part of the or bottom top part of the cohomology with respect to the A grading, and you need more work to get another grading. So to get the full grading, and the idea is that you need to do, instead of simply identifying this, you need to do some monodromy around the origin to get the rest of the A grading. Okay.
Can you explain again the remark about matrix coefficients? What are the kind of rows and columns in the matrix
The row, you fix this flag and you fix this flag.
at the top and the bottom of the
Yeah.
picture? Okay.
That's the matrix coefficient. But if you close the picture up, there is nothing else to fix. You simply go over all flags here, but they must coincide because of the rules of the game. It's like a trick. Mhm. So let's right. So now let me. So you see that we already can produce some pictures, some circular pictures in this. Sorry, one more thing. So one remark. If you use merge or split, you get compact variety. If we only use merge split, you get compact variety. And so this corresponds to the case of target by models. You know, one of homology setup, and then if you use is this, then this is already non-compact. So to compute this cohomology, you have to use compactification and get this complex of surrogate by models. So, okay. Now let's start slightly different direction. Maybe I stop here. It's not very important for this piece of motivation. So, Right, well, so now I want to go to. Going to affine. Here. And affine. You know. So how do you do this? The answer is you just draw. So the diagrammatics is the following. You draw the same sort of diagrams, but on the cylinder.
Just, you said when you talk about the braiding, you get a non-compact variety. If you compactify, do you get the merge and split, and then that one?
Yeah, you get this minus this.
So the minus is the extra stuff you put in the compactification.
Yes. It will be converted for the cohomology, it will be converted into a complex. That's what was mentioned. Yeah. So diagrammatics is same diagrams on the cylinder. And if you want to do double affine, I will just to kind of go several steps ahead. It will be same diagrams on the torus. Torus, almost there. But that will come later. So there are two ways to draw the cylinder. One way is this sort of way, and then you identify alpha and alpha prime to get the cylinder, but because later I will have to draw some things on the torus, I want to reserve to give you another way to be able to use two directions. So the second way is that I kind of still draw. I think that our blackboard is secretly is R2 times S1. So there is this extra direction that this direction comes perpendicular. And it comes in our face and then somehow reappears from the back of it, right? Because it's S1. So then every diagram is a combination of arcs as before, but then draw. So we interpret this kind of the loop that kind of goes towards us and then reappears from the back. We draw a dot on the line. So now arcs will have dots. So here is a dot, and the meaning of this dot is that it's kind of makes this sort of, I don't want to say that, sort of like this. If you look from the side, make it drop. And so this is towards us. So kind of comes here and then comes again from the back of the blackboard. So that's the meaning of the dot. And all other pictures are remain the same. We can have merge, split, and intersections like this. Yes.
So you've talked about doing these diagrams on a plane, on a cylinder, and a torus, which are all framed surfaces. Is it necessary that you have can you imagine making sense of the combinatorics of the diagrams on, say, a genus 2 surface?
I don't know. I mean, we can try to make sense of it. The question, what do you want to do afterwards? So, yeah, I don't
It's
know.
not something that you, it's not something you'll talk about.
But, maybe, yeah, I don't know. So this is the rule of the game. Now, what kind of relations we have? So actually, there are no new relations. So for example, in the affine Hecke algebra, let's do affine Hecke algebra. Not the affine quantum group. But affine Hecke, you have something like this. This is sigma I. And let's try to do and this will be this is dot. This is let's call this xi. This is a notation for dot on the I strand, and then xi plus 1 is a dot on this one. And then you can imagine that so let's do sigma I. I sigma I. And you see that you can simply undo this loop because this goes up and then simply reappears from below, so you can slide it over. Plus 1. Yes. So that's this way you get the affine Hecke algebra relations. So this is generated by. So there is some slight normalization issue that will make it slightly different. But so here is a different preferred normalization. So the generators are x1 and p1 pn minus 1 and even so like this, and well, the xi's commute. And we have sigma I xj commutes if j is not equal to I or I plus 1, then you have sigma I xi sigma I plus. So normalization this one, and then I think the rest is simply the usual Hecke algebra relation. Okay. Well, let's now think about how to interpret these pictures using flux.
Sorry to interrupt, but when you say that this, if you merge split and compact variety, you get the dependent on non-compact complexes. So which variety are you referring to?
So the variety is parameterizing configurations of flux given by all these conditions. What else?
Not of a finite field, just complex.
So you can, for finite field, it becomes finite set, but It just conditions are algebraic equations on the flags,
Okay, okay.
on subspaces. It's just lots of subspaces, one inside another.
Ah.
Sometimes one is not equal to another. When you have this, when you use sigma I, you have to say that this flag has to be different from this.
And what do you do to this variety again to get European bimodules? For example?
You take its cohomology.
I think it's okay. Okay.
There is also Borel-Moore homology, and they give you slightly different version, but they both work.
And again, and to get complex algebra bimodules, you need cohomology with some different.
Let's say let's take Borel-Moore homology. Then it turns out that these compact varieties have pure. Therefore, the cohomology of the complement is just computed by just one differential between two things.
So in the non-compact case, the differential comes from, you say, from Lefschetz class.
So you have a if it's just two varieties open and closed, then there is a long exact sequence. And because of purity, it is just combination of short exact sequences. If it's not just two open and closed, but more complicated, you have to remove many stuff, then it's you kind of use this short exact long exact sequence several times, or you do spectral sequence, you get some complex of things. And that computes the cohomology of the things. So, right. So now what do we do? How to get the geometric interpretation of these pictures with dots? So how to get dots? Well, so this is basically this is Lustig's construction. We imagine, but let me try to kind of build up to it. So remember that we had this flag variety. All right, I called it flag. And right, and then we had also Gmod P, PA when A is a vector. Position of N. And then so let's, I don't know, consider it XA. And then there were like maps between them, XA, prime, and I don't know, something like this, maybe this one. So remember that merge was a map this way, and let's say we have some another, and we have split. It's mapped backwards. So it is a standard thing to interpret this counting points over finite fields as giving you some sheaves corresponding to some elliptic sheaves on these spaces, and maps pushing forward and pulling back give you certain functors between sheaves. And that's kind of, you can follow this route and give another approach to kind of, you will obtain a computation of the cohomology of that variety in the sort of geometric way using some functors between sheaves. But let's do something different a little bit. So I want to replace this set of points over FQ, and we remember we were looking at linear combinations of points over FQ by the K theory. Of the space. And then, right. So why do I like this one? good point already is that I know what to do with the dots. Because so space so this flags, but it also works for arbitrary A and for all these merges, just that the dots are more. Yeah, so in this case, so all lines have thickness 1. The space has line bundles. There is precisely corresponding to the jumps in the whose fibers over over a flag. Over a flag like this are Fi mod Fi minus 1. Yeah, this is a point in X. It's called X. Yeah, so already I can try to so already we have an action of these line bundles on the so this will be all them 1 n, and so we get the multiplication by these line bundles in the action on the K theory. So the dots now correspond to tensoring by this Li. So there are many relations are kind of start automatically. For instance, yeah, well. So now what do we do with the maps between varieties? Which split. I interpret it as follows. So we have, let's say we have variety where we have 1, 1, 1, 1, 1. 2, sorry, 1. And then we have merge, so EI. Then it becomes X 1, 1, 1, 1, 2, and 1, 1. So and then we have this map. So what we can do with this map is simply a relative P1 bundle. So it's proper, and we can push forward along PI. So and then this one, so this one is we just pull back along this one. So imagine if I have a vector bundle here, I will compute its relative like Euler characteristic, so to say, or take resolution, take push forward, and then replace the resulting complex by alternating sum. And here I just take any vector bundle and I pull it back. But this is does not quite work. Because things don't match the way we are expecting them to. Suppose we do this picture. First we do merge, then split, and then merge again, and then split. So what do we do? here, we, let's consider this part. The diagram, and we need to get, remember, we need +1 for this part of the diagram. And this part of the diagram means take the one some 2, 1, and then this is a complete flag variety. And then again, so this arrow is the same as this arrow actually. So we insert flag in all possible ways and then forget it. So we simply have this relative P1 bundle, and we do this operation, pull and push. And that's you can use, for instance, projection formula, and then it's enough to see what happens to the structure shift. And if you do pull push by structure shift, you just press structure shift here, push forward. Other characteristic of the structure shift is 1. So you again get structure shift. So the problem is that obtain 1 instead. And then so the way to rectify this problem is to, whenever you take push forward, you have to a solution. So we want to get P1, then Q plus 1 is the number of points on P1. So you think Q plus 1 is H0 of the P1 minus H plus H2 of P1. And this is H0 of the structure shift. And this is H1 of the differential forms by Hodge theory. And so you get the same answer if instead we will compute so whenever we take push forwards, we will twist by the relative Durham conflict. And then everything works the same way. So instead of what was the by upper star, whenever we have map from Y, X, we use by upper star of something tended with the relative with the alternating sum minus 1 to the I of Y over X. So, and we need Q.
You said out loud pi upper star and then you wrote pi lower star. Do you put a lower star to denote upper star?
Upper star.
You mean lower star?
Lower star.
Sorry, stupid question. What do you mean by this equality? Q plus 1 is equal to H0 of all P1 minus H1.
Well, it holds in many ways, right? One thing you can say is that one is the union of A1 and the point. The class of a point is here, is a generator here, and A is here. Or you can say there is a Frobenius acting on the cohomology, which gives these eigenvalues. Yeah, so there is weight theory. So we use this instead, and that will give us the right answer.
That's why the minus sign, right? It's all the characteristic would be H0 plus H2.
Yeah, so let's compute it. Let's see. Let's be careful. So let's try P1 to a point. Then we will have 1. We have OP1 minus Q omega. Then this characteristic is 1, but this characteristic is -1. works. No, but it has to work. It's just so in the case when variety is smooth projective and it has number of points is given by polynomial of it will always work. By what
Just your notation. You're saying push that forward, but then also pull it back after that, right? Pi upper star or pi lower star.
I'm saying replace push forward by this.
Then you want to go back to y, don't you?
That you don't do any, you just pull back.
Okay, that's what I.
So, okay. And then you check relations. Relations, they work. So, so there is some slight modification of this. Which is that, as you may guess, that instead of working with varieties, we can work with symplectic varieties. So, replace x, y by cotangent bundles of x. And put some equivalent parameter in the cotangent direction. Then, so meaning that you have torus corresponding to parameter q acting here, and q actually corresponds to one-dimensional representation of the torus. So then K theory of X tensored with functions in Q. It's simply K theory of the equivalent K theory of the bundle. Then if you have f from x to y, you have to look at the corresponding Lagrangian correspondence. And you have I don't know, z f, and that is the f, and then there is t star x, t star y. You can pull along this correspondence without any correction. And then you can check that it gives you the same result. But up to some twist that people always keep forgetting that entering by dualizing so canonical one. That's sort of from this perspective, we should expect that we can replace our so we can replace our G mod PA with the corresponding cotangent bundles and do the same sort of like before and get again action of fine. So instead of passing two spaces like G mod PA, K theory, and K theory of the spaces, we get same action. Well, this is a theorem by someone because these are Nakajima varieties. An action of affine UQ and GL and that and affine Hecke algebra. Yes.
Is this the key version of what Kavanagh and Thomas did some time ago? Braid group action on unit sheaves over flag, right? Contingent bundles to flag, right?
I don't know.
But it was done. It was done much before.
That's okay. So this is how we arrive at one affinization. Now we can do another way, kind of another approach to now, but towards double affine. U Q G L. So roughly speaking, this algebra arises by drawing the same kind of diagrams on the thinking that instead of we have our time evolution and each slice. Now we started with a disk, and we had this sort of a circle or annulus, and now we have to do a cylinder. So we should allow now. So way to visualize it is to draw our diagrams on the diagrams. Now will are on the on this, where we glue together these two sides of the picture, and we also additionally to this we allow dots. So but before maybe introducing the algebra, let's already start talking about its geometric interpretation. So we kind of already use the ability to put dots, use the ability passing to K theory of the cotangent. We now allow ourselves to put dots. Now we should use the cylindrical structure of the picture, and the way to do it is if you have any picture in the strip, you just interpret it as a periodic picture, or periodic picture. And okay, let's go further. So if we have a periodic picture, and then we have if you have some lines here, we should think about them as flags. But now we arrive at an infinite flag, and so consider infinite flags now. Or if we, so, and the natural mathematical way to think about them is either you, so that's how you get the fine flag variety. What is this? This parameterizes. So now our vector space, consider C. But so yeah, the notations like standard notations. This is T. Oh wait, T will be used for analysis. So let's call it Z. And then K is Laurent series. And then we have A to the N. And then we consider infinite flags. Here. Flags. So let's start with writing F0 somewhere. 1. Now they go all directions. That's satisfying that two conditions. So first condition is that Fi is a lattice. So in other words, it is free or module of rank n. And second condition is that this sort of periodicity condition is that Fi plus. Now, I don't want to kind of restrict myself by, so there is also number K. And I want to fix that I plus K equals Z inverse of I.
What's
The parameter.
I'm actually a little confused. I somehow thought that you just have a flag and C to the N and you have a monodrome, and somehow every time you go over, you just apply this monodrome to the flag. Can you think about it this way as well?
So some other picture, but this is
It's unrelated to what you're saying.
no, it is related, but the relation is it's tricky to explain. Let's just not spend time on it. So yeah. Okay, so again, the data also is a couple of numbers. And notice that this flag, modulo this flag is precisely n, so this is to be n. Yeah. So now we have this, yeah, so we can do two things. So naive thing first, we can do this all over finite fields. What we will see, well, everything works, all relations will work. We have some pictures and merge and split, makes sense. And so we can obtain action of the of whatever algebra we want, a fine algebra. Obtain U GLN hat or find Hecke action M. So this will be K as before, the number of find Hecke and act when this when AI equals to 1. Okay. So the proof is the same. But over with K theory, over the complex numbers is more interesting.
What is this action on? What is the object it's acting on?
So we, for instance, we get the action on the functions on a few points of the.
But it's not finite, right?
Let's say finitely supported function. Right, I mean, it's not finite, but it's sort of not very infinite. You can kind of cover it. So more interesting. And why is it getting more interesting? Because we can introduce another parameter. So let now T be so the torus CT act by scaling Z. Then what we see in this is that f I plus k plus 1 f plus k modulo f I plus k minus 1 is not quite isomorphic to this line bundle. There is this z here, and so this forces that xi plus k equals inverse. If you think about line bundle corresponding to the jump, and this will give us a couple of Hecke algebra. Obtain Hecke algebra, and so I mean, no, I guess it would be too long to write relations. But relations are so this is given by generators sigma 0, sigma n, and x 1 xn, and then they have, well, you introduce a rotation which just sort of slides your flag to the right or left. It's cyclic shift. Then you have this satisfy the affine Hecke algebra. This satisfy so this together with n sigma 0, sigma 1, sigma minus 1 also satisfy affine Hecke relations. And then there is one relation that, so you simply think that xn plus 1 equals the T inverse n to get the extra relation. So this is related to results of Morton Samuelson, namely that the Sodaha is isomorphic to this diagrammatic algebra. And you should think about the torus, and there is a marked point, and the rule of you have some diagrams, points walking on the torus, but going around the mark point costs you the price of writing T inverse. So now if we now how do we say that? So if we do a dot here. Or if we kind of go to this side and do a dot here, then the this is TOT inverse. And the way to, you should imagine that here somewhere there is a one line, the image of the trajectory of this marked point. Trajectory. There. So that's explains the grammatics of the fine Hecke algebra and how to find their actions in geometry. Oh, okay, I have to stop, right? Yeah.